Okay, so there's a bunch of arithmetic associated with pages. So there's sort of three different numbers, right? There's a number of bits in the page offset, the number of bits of virtual page number, and the number of bits of physical page number. And there's all these sort of mambo combinations here. The big thing to keep in mind is that I need 2 to the v entries. I need 1 entry for every possible virtual page number. So if I have v bits of virtual page number, I have 2 to the v different combinations of those bits. So I have 2 to the v different possible indices into my page map. So my page map can get big if I choose my page size to be small. Okay, so down here we talk a little bit about, well, you know, on the beta and certainly on machines of the not too distant past, the entire virtual address was 32 bits. The physical addresses have been changing over time. It used to be that, machines that you bought a decade ago, could only address a couple gigabytes of memory. Modern machines can probably address, they usually now are about 2 to the 40th. They have 40 physical address bits, so they can address. So let's see, 4 gigabytes is 32 bits, so 256 times that. So modern machines can address about 1 terabyte of physical memory. The latest generation of machines have 48-bit physical addresses, so you can address 256 terabytes of main memory. That seems like a lot, and indeed it is. I mean, but some of these data sets that people are dealing with, particularly in the fields of biology and stuff like that, they're so huge that that number is, sort of what we can afford to put on a machine, but that number is already seeming small in terms of the size of the data sets that we're dealing with, so quite remarkably so. Okay, so as usual, our little friend is asking a pertinent question. Suppose my virtual memory and my physical memory are the same size. Would I even need an MMU? What advantages would I get for having an MMU even in that case? In other words, where I might just leave out this translation. And so think about that. We'll come back to that in a second. Okay, so just to look at some numbers here. Here we have a 32-bit address with a 12-bit page offset. So how many bytes are there on a physical page in this machine, the one that's pictured here? How many bits of page offset are there? 12. So how many bytes are there on a page? 2 to the 12, or? 4096. Thank you. So one of the things you will know by the time you graduate as a Core 6 major is the powers of 2 up through a pretty large number. So, okay. Alrighty, so 4096 bytes on a page. How many virtual pages are there in actual decimal? What's 2 to the 20th, roughly? I don't know. 1 million, exactly. So this is 1 million. So how big is this table? How many entries does this table have? Well, it has 1 million pages. There's 1 million pages, so I need 1 entry for each of the pages. So this is a pretty big table. This is a 1 million entry table, right? And then down here you can see I have an 18-bit physical address, physical page number. So the total number of physical pages is 2 to the 18th, or 256. This is actually a pretty dumb little machine. I mean, your watch probably has more memory than this. Okay, the number of virtual pages we already discussed. We have 20 bits of virtual page number, right? So what I did is I took 32 bits altogether and I subtracted off the 12-bit page offset, right? So that left me 20 bits that had to be on the other part. So together, the virtual page number and the page offset cover the entire virtual address. So we have 2 to the 20th pages. We have 2 to the 20th page map entries. And we need, let's see, so we have 18 bits plus the R bit plus the D bit. So we have about 20 bits per entry. So we have about 20 million bits of information in our page map. That's actually a lot to stick into, that's actually not a small piece of DRAM. So we're starting to say, well, conceptually this was a very clean picture. From an implementation point of view, perhaps this is a little expensive. This MMU, which was meant to be this neat thing, is actually turning out to be as expensive as all my caches, my CPU, maybe even if you're buying a lot of static RAM, you could buy a lot more physical RAM for the same money. Static RAM is pretty expensive. And plus it's a power hog. Okay.